And let's, oops, push the wrong button. Let's try that again. Let me start sharing my screen. Let me make sure in that screen share that I can still see the chat. And before we start picking up with the notes, is there anything that anybody wants to look at from the homework? Does anybody have questions on any homework problems?
Yes, number 10.
Number 10 in which homework? The one that's
Section 3.
Section 3? All right,
Yeah.
there was a little bit of Section 3 that we had not gotten to. And
Oh,
so
okay.
I took the liberty of pushing it back. But let's go through and let's start by looking at that question number 10. Because if I remember correctly, last class, in this section, we had gotten through simplifying a radical and adding and subtracting radicals, but we had not looked at rationalizing the denominator. And so I know there were questions in this homework that deal with that. And actually, I was going to give a quiz after today's class, but because we hadn't really finished rationalizing the denominator, it will be given after Friday's class. So question number 10.
Yes.
My internet is not letting me switch question numbers easily. Let's see if it lets me do it now.
Wait, so we have a quiz after class?
On Friday.
Oh, okay.
For our homework, are we supposed to submit our work to your email or anything?
No, you only submit the work for tests and quizzes. Yeah.
Oh, okay.
Question 10 starts where we're going to be looking in a couple of minutes. Can I use that as an example? Let me write that down now. So we'll look at that one in a second. Did anybody have questions on any other homework questions?
Yeah.
Where?
Question 8 and 11.
Question 11 is the next one, so let's go there. 11 again is like what we're going to look at today. So we'll, it's very similar to the preceding one, so we'll look at that as an example also. And question 8. For question number 8, what we're doing is we're multiplying radical expressions. And so we've got the square root of 6x squared times the square root of 24x. We had said that when you multiply radicals, as long as they're both the same radical, the same root, we multiply the radicands. So 6 times 24 is 144. And then x squared times x is x to the third. Now what we have to do is we have to simplify. 144 is a perfect square, so I can take its root. X to the third, we had said that if we have an even exponent, it's a perfect square. And if we have an odd exponent, it's not. So that x to the third, we're going to break up into x to the second times x. So we'll take the square root of 144, the square root of x to the second, and the square root of x. The square root of 144 gives me 12. The square root of x squared is x. And now this extra factor, it's not a perfect square. We cannot take its root, so it stays under the radical. And so our final answer is 12x radical x. Better, Marcus?
Yes.
Okay. Anything else? If not, let's pick up from where we left off. I think we left off, we were adding and subtracting radical expressions. So let's go through and let's look at that division and rationalizing denominators. Now, if I remember correctly, we had said that if I have the square root of a over b That's equal to the square root of a over the square root of b. And we had said we never wanted to leave a fraction underneath the radical. We also said we never wanted to leave a radical in the denominator. I'm going to pick up that first example that we were looking at, the square root of 196 x to the third over the square root of 4x. Here we've got that radical in the denominator, but this time I'm going to put them together using that quotient rule backwards. The square root of 196 x to the third over 4x. I can combine them because they're the same radicals of both square roots. Now I think I can divide this fraction out. Does 4 go into 196? I believe so. I think that that goes in 60. Oh, help me out here.
49.
49 times? Hello.
Yep.
That's what happens when I try to do division in my head. 49 times.
I got
And
you.
x to the third, x to the second. And now they're both perfect squares, so I can take the root, and my final answer there will be 7x. Let me go back and I'm thinking that one that you were asking about, Marcus, was more of the same. Let me go back and pull up that number 11 also. Number 11 was the square root of 200x to the 10th over the square root of 5x. So if I take the square root of 200x to the 10th over the square root of 5x, well, they're both the same radical. So let me first start to see if when I put the two radicands together underneath one radical, I can reduce that fraction. And yeah, 5 goes into 200. That would go in there 40 times. And x goes into x to the 10th, x to the 9th time. Now what I need to do is simplify that. So where I have that 40x to the 9th, perfect square that goes into 40, I believe the largest one is 4. So that's 4 times 10. Now x to the 9th, because it has an odd exponent, it's not a perfect square. The closest perfect square would be x to the 8th times x. Again, we had said if we're looking for the square root and we have an odd exponent, we always take one factor out. We can take the square root of 4, we can take the square root of x to the 8th, but that 10x we cannot take the root of, so they stay underneath. The square root of 4 is 2. The square root of x to the 8th is x to the 4th. Because again, last class we said if we're taking the square root, second root, we divide the exponent by 2. And then we're left with the 10x underneath. And so this would be the final answer. So far, so good.
Yes.
Then, also in rationalizing the denominator, if no radical in the denominator, and the fraction does not reduce, what we do is we're going to multiply both the numerator and the denominator by the radicand in the denominator. Although sometimes we can multiply by something smaller, sometimes we're going to multiply it by the smallest radical. It makes the radicand a perfect square. Radicand in the denominator. And then we're going to simplify. The second step is much less writing than the first step. Let's start with a pretty straightforward.
Well, 1 second, please.
There's where I was going next. Should I wait a minute before we look at an example? Let me know when you're ready, okay? Let's start about as simple as I think we can make them. Can I look at 1 over the square root?
Makes
Ready? Now, this idea of rationalizing the denominator, the way in which I justify it is never wanting to leave a radical in the denominator. It's way back when I was a child, pre-calculator days. If you had to divide something like this out in your division, you'd have 1 on the inside and this crazy long decimal on the outside. And that division would be painful to do. If we rationalize the denominator, we're going to come up with something that would have been much more easier to evaluate. And that's become standard practice now. So international rules, never leave a radical in the denominator. My denominator is radical 2. So I'm going to multiply the denominator by radical 2 and the numerator by radical 2. Whenever I do this, I always take the time to write that step out because I want to make sure that I'm multiplying numerator and denominator by the same thing. Because notice anything over itself is equal to 1. So I'm just multiplying by 1, which means I'm not changing what it's equal to, just what it looks like. Lincoln, whomever else, I did move that assignment back because we hadn't covered all of it. So now when I multiply straight across, 1 times radical 2 is radical 2. Radical 2 times radical 2 is radical 4. Now I can simplify that into the square root of 2. And the square root of 4 is 2. And so this would be considered simplified form. It has a rational denominator. And back in ancient times, when I was doing it by hand, my divisor would have been 2, which would have made it a much easier division to do.
Wait, so so basically after you square root it with the denominator of 2 and the numerator of 2, so you would just basically multiply across and then that's how you get your answer?
And then simplify what you can. Please.
Okay.
That, well, this looks like it's 2 over 2. 1 is under the radical, 1 is not. So I find them. So that's done. Let's look at a few more examples. Let's look at the square root of the fraction 2/3. Well, I can't reduce that fraction. And I can't leave a fraction under the radical. So I'll look at that as the square root of 2 over the square root of 2. However, I can't leave a square root in the bottom, in the denominator. So I'm going to multiply both numerator and denominator by radical 3. I'm going to stop there for a second and ask, is everybody okay with what we've done so far?
So
Can
the
you just leave it
next,
up there for a little bit?
Say that again?
Can you leave it up there for a minute, please?
Not done yet. Yeah, we're going to leave it up.
Okay.
Okay. Somebody else was
so
asking.
after you change the square root over to the other, how do you get 3 over 3? You said you multiply.
The denominator is radical 3. I don't get radical left in the denominator. So that's what I decide to multiply by, radical 3.
Okay, how do you get the square root of 3 on top though?
Because I don't want to change what this equals, right? I just want to change what it looks like. And so I have to multiply. The only thing I can multiply, not change what it equals, is the number 1, yes? And so by putting radical 3 over radical 3, by doing the same thing to the top and bottom, you see how technically I'm just multiplying by 1. So whatever by the denominator by, we must multiply the numerator by the same thing.
So basically, like, whatever the on like in the first problem, whatever the denominator is, that's what you divide. That's what the fraction you make for to multiply.
Yes. Sometimes there are other things that you can use that give you smaller numbers, but if all else fails, you can always take what that denominator is. I wrote too much over there, so I'm going to rewrite it down below. The denominator is radical 3, so I'm going to multiply the denominator by radical 3, and I must do the same thing to the numerator. So far, so good?
Okay, I somewhat understand it a little better now.
Okay. Everybody else okay too?
Is there any way you could go just a little bit slower?
Sure. Are you all right now, Ashley?
Yes.
Okay, so now let's multiply across. The square root of 2 times the square root of 3 is the square root of 6. In the denominator, the square root of 3 times the square root of 3 is the square root of
9.
9. Oh, wait a
And
minute.
then wouldn't you divide that by 3 and get 2 over 3 again?
No, because that undoes what we just did. Instead, I want to look at this and say, what's the square root of 9?
Regular 9.
Well, what's the square root of 9?
3.
3.
Plain old
Oh.
3. And so now this is my final answer.
Oh, so basically, like, once you get to that last step where you have both the radical 6 and the radical 9, you would just divide the,
Radical.
you would just take the square root off of the bottom number.
You do whatever you can simplify, you do. It's not
Okay.
a process, just take the square root. It's whatever you can simplify, you have to simplify.
So if you
Okay.
can simplify the top as well.
Yes. And we're going to look at that in the next example. Okay.
Okay.
So, ready for the next one, folks? And this is considered simplified because international laws, no radicals left in the basement. It's kind of like no skeletons in your closet, no radicals in the basement. Let's look at 2 over the square root of 18. I want to do this one twice. Once a very rote way, but it gives you a little bit more work. One where it takes a little bit more thinking, but overall it's less effort. By what we just did, we have a radical in the denominator, 18. We want to get rid of it. Is there anybody who would just go through and multiply numerator and denominator by radical 18? Because that's what we've been doing. That gives me 2 radical 18. And I'm sorry, I don't want to work that hard. A little bit of a headache here. Is everybody all right with the idea that if I take the square root of 18 times the square root of 18, I'd be left with plain old 18? When we multiply a radical by itself, we take its hat off. Is that idea okay for everybody?
Wait, so, my bad, Lonnie, I didn't mean to cut you off.
You're chilling.
But, so basically, like you said, so basically when you multiply the same denominator, depending on what the situation is, it's just you take the square root off, or if it's like this type of problem, that's how that happens.
Whenever I multiply a radical by itself, up here in the above example, when we took the square root of 3 times the square root of 3, we did a middle step, but didn't it just give us 3?
Yeah, we
Yeah.
had to multiply that, and it gave us 9, and then take it out, and that gave us 3.
That's always going to happen. If you think about it, if I were to, I'm looking for a place to do a little bit of scrap work. If I were to take the square root of a times the square root of a, wouldn't that give me the square root of a squared, which is just a? Whenever we multiply a radical by itself, we're squaring it, and so it undoes the radical, so it just takes the hat off.
So is that equation simplified then? It's just 2/18 to the square over 18?
Well, thank you. I stopped for a minute to explain, but yeah, this has to be simplified. First of all, can anybody just reduce the fraction? 2 over 18, does that reduce?
What? Well, the top part wouldn't.
1 to 9.
It's just 2 times 18, right? It would just be 36. I
Well,
mean, not 36. Yeah, it
we
would be
can
36.
multiply them because one's in the radical and one isn't.
Oh,
But
okay.
can I reduce the fraction 2 over 18?
1 over 9.
So doesn't this become radical 18 over 9? But I still think I can simplify this more. Is there anything that goes into 18 that's a perfect square?
It was all the not. Oh, so wait.
So that, can I think of that as 9 times 2 over 9?
So does it become 1?
No, because this one's underneath the radical and the other one isn't. I'm sorry, I'm going to move the chat box. It's in the way right now. Ooh, that was not a good way to move it. I'm going to minimize the window for a minute. So I'm going to take that as the square root of 9 times the square root of 2 over 9. What's the square root of 9?
3.
3.
Doesn't this become 3 radical 2 over 9? And can we still reduce that fraction?
What?
Yes.
Yeah.
It would be 3 radical 2, wouldn't it? I mean, not 3.
Let's see. When I reduced, isn't the 3 left in the denominator? And so that leaves
Yeah.
radical, oops, it would help if I wrote what I'm thinking. Radical 2 over 3. Okay, is there anybody else who looks at that and thinks that one had way too many steps?
Yeah, but
Yeah.
because the part that kind of confused me was when you got to the 2 and then 18,
Uh-huh.
and then I see that you had put it as the square root of 18 over 9.
Right.
And so basically you took the, oh, I see what I kind of see what you did now.
18 reduces to 1/9. And
Oh,
because I'm lazy and I don't need to write that one out front, I did.
okay, I
Does
can
anyone want to see a
kinda
shorter
see.
way of doing this one?
Yes, please.
Well, we've got that 2 over radical 18. Is everybody familiar with the idea that 18 times 2 is 36?
Yes.
So I'm going to, instead of multiplying by radical 18, I'm going to multiply by a smaller number, radical 2. That'll leave me with 2 radical 2 over the square root of 36. And now I know 36 is a perfect square, so I can take its root. And now, can we reduce that fraction 2 over 6?
Okay, that's kind of easier because it's kind of like how you've been showing the
Yeah. It's easier, but the problem is it takes a little bit more thought to come up with that radical 2. If you
right.
come up with a smaller number you can multiply by to get a perfect square underneath, fine, it makes less work. However, I know there's some people who aren't real good at coming up with this 2 to get to 36. And so I just wanted to show you that you can always just multiply by the same number that's underneath. Just sometimes that makes a little bit more work.
So if we ever did come to something like this, and if we can do it either the first way, like that you showed us how to solve this problem, or the second way, it doesn't matter.
It doesn't matter. Both take you to the same place.
Okay.
It depends on what your number sense is like, how good you are with knowing your perfect squares and knowing your times tables, which one's easier for you. Okay?
Right.
All right. Let's do one more of these. I'm going to shut up and have you folks do it. This one's not quite as challenging as that last one. But let's look at the square root of 7 over 3. And I want you to please rationalize the denominator. Now I'm going to be quiet for a minute and let you guys do this one.
Mm.
Did anybody else get what I got?
I had put 9 for my denominator.
Right, you got the square root of 9 in the denominator.
Oh,
But then the
okay.
square root of 9 is 3.
So
In
then
between,
21 over. Oh, okay. I see.
in between times, you might have written this as the square root of 21 over the square root of 9, which would then simplify into the square root of 21 over 3, which is fine.
Okay, I see.
But this is going to be our final answer because our whole goal is to have no radical in the denominator.
This is kind of easy in a way.
Okay, so let's get to the harder ones.
Oh boy,
No.
I shouldn't have said anything.
Everybody all right with this one so far?
Yeah.
Can you give another example?
Sure. Do you want to give me your number?
Yeah.
What's your favorite number?
I should pick a number?
Yeah, pick a number.
8.
So let's say we have the square root of 8 over, oh, you know what? Let's make this one fun. Let's say we've got the square root of 8 over the square root of 10. Before I do anything else, does anybody see anything with that fraction?
They're perfect squares.
I was about to say they're perfect squares.
No, they're not. What can you square together?
Oh, 10's not a perfect square.
No, neither is
Here's
8.
8. So,
They're both
Oh.
even though, right? Can't I reduce that fraction?
yeah, it's a 4/5.
And so then when I change that into the square root of 4 over the square root of 5, what else can I do?
You can
Get
take
rid of the
this.
square root on top.
Yeah. So that would just make it 2 over
Yeah,
5.
4 would be 2 over square root of 5.
Right. Are we done yet?
No.
Because
What?
it's the square root in the bottom, right? We can't do that. So to get that radical out of the denominator, what do we need to do?
So wouldn't we have to do what we did in the first problem? And I mean, not the first problem, the problem before the first one you had us do by ourselves, and get rid of I forgot how we got rid of that square root.
What would
Multiply the 5 over.
You multiply
radical
by
5
square root of 5.
Yeah.
beautiful. And so that gives me 2 square roots of 5 over, this would be the square root of 25, which is just 5.
And then
And then we're done.
oh
That's the final answer.
yeah, because it's 25. Okay, I see.
Okay?
Could you just say, instead of saying 5 times, is it 25? Since they're the same one, can't you just say that it's 5 because of that?
Right. When you multiply a radical by itself, you just get the radicand. So there's 2 types of people in the world. There are people in the world who can see radical times 5 times radical 5 is 5, and that's great. If you're not one of those people, hopefully you can see that that would give me the square root of 25, which is just 5, so it takes me to the same place. Either way, it takes you to the same place. All right? If so, we have a question. I have a question to ask. What if there are 2 terms in the denominator?
Oh, that's a good question. I don't even know.
What if I have 1 over the square root of 3 plus 1? I've got a square root in the denominator. Damn it, I can't do that. What do you folks think I'd need to multiply this by to get that square root out of the denominator?
Multiply by 1 on the top, and on the bottom to cancel out the bottom. Then we multiply the top, it would change the top number. Then you just have a radical on the bottom.
We can't have a radical in the bottom, so we've got to get the radical out of the bottom.
What did you multiply by the square root of 3?
Well, let's see what happens if I multiply it by the square root of 3. I'll do the hard part. In the numerator, 1 times the square root of 3 is the square root of 3.
Oh, okay.
But in the denominator, in order to do that multiplication, don't I have to distribute?
Okay, so would you
So
just
radical 3 times radical 3 would be,
9, the square root of,
which is 3.
okay,
And then I'd have radical 3 times 1, which is,
radical 3?
so I still have the radical left. Did that help me at all?
Not really.
No, so that's not going to work. In order to be able to do this, we have to define something, and that's called a conjugate pair. And before I define a conjugate pair, I want to see if you folks can remember what happens if I take A plus B times A minus B. Can anybody at all remember multiplying a product like that out where we take the sum and difference of the same terms? Can anybody remember at all what you get? Do you guys need to FOIL it out or box that out, or can anybody remember the shortcut rule for that one?
Maybe.
Wouldn't it just be AB and then negative AB?
Not quite. Does anybody remember that that gives you A squared minus B squared? When you have the product of the sum and difference? If we were to FOIL, first is A squared, outer is minus AB, inner is plus AB, last is minus B squared. The middle terms cancel each other out, and it gives me the difference of squares. So we're going to say that A plus B and A minus B are a conjugate pair. And their product, A plus B times A minus B, gives me the first one squared minus the second one squared. Those are variables. What does that have to do with the problem that I wrote up above?
Because you have to distribute with the conjugated pairs.
You take the squares of both pieces. So let's first ask, what is the conjugate of radical 3 plus 1?
Radical 3 minus 1.
So it's radical 3 minus 1. So we're all in agreement there. And if I multiply radical 3 plus 1 times radical 3 minus 1, that would give me, using the pattern, the first one squared minus the second one squared. And when I square radical 3, what do I get? Isn't that just 3?
Just 3.
And when I square 1, I get?
1.
And so I'd be left with 2. And so if I multiply a binomial expression that contains a radical with its conjugate, there's no radical left. So to rationalize the denominator of a fraction with a binomial radical expression, that's a mouthful. And I'm sorry I'm writing slow today because of my hands. To rationalize the denominator of a fraction with a binomial radical expression, we're going to multiply both the numerator and the denominator by the conjugate of the denominator. Does everybody have the words down? Can I turn the page to
Oh,
No.
1 second.
Sure enough. And again, if you have a hard time keeping up writing the notes, you can just pay attention because I promise the written word will be a PDF in Blackboard by the end of the day. Can I turn the page now, guys?
Yes, you can. Thank you for waiting.
So if I have 1 over, what did we start with? Radical 3 plus 1. There's 2 things in the denominator. So I've got to do the conjugate. The conjugate of radical 3 plus 1 is radical 3 minus 1. But the only number we can multiply a fraction by is 1. So whatever we do to the denominator, we've got to multiply by the same thing in the numerator. Here in the numerator, when I multiply by 1, I just get that radical 3 minus 1. In the denominator, because they're conjugates, it's the first one squared minus the second one squared. And so that leaves me with my numerator is radical 3 minus 1. My denominator is 3 minus 1. So my final answer is radical 3 minus 1 over 2. And this is considered simplified. If we were to have to do any sort of computation with that original fraction, it would be easier to do it in this form. Shall we try a couple more of these?
Yes.
Let me take radical 7 over radical 5 minus radical 2. Wow, that's chock full of radicals. Does everybody notice that there are 2 terms in the denominator? Because there's 2 terms in the denominator, I need to find the conjugate of the denominator.
So when we add the bottom, since it's a subtraction,
Yeah, so it'll be radical 5 plus radical 2. And whatever I do to the denominator, I have to do the same thing to the numerator. Which would you guys simplify first? The numerator or the denominator? Would you work with the tops first or the bottoms first?
the bottoms, right?
But it doesn't make a difference. Bottoms, because they're a conjugate pair, it turns out to be the first one squared
And then minus the second one squared.
but that's just going to be 5 minus 2. So my denominator,
Is 7.
ooh, minus 3.
Oh, wow. I'm sorry.
Don't worry. I do careless things too. Now in the
And-
numerator,
So wouldn't that be the square root of 35 and the square root of 14?
right? Square root of 35 plus the square root of 14. And I don't think either of those finish. Simplified, pardon me. So I'm finished.
Okay, now I'm kind of seeing how to do this a little bit.
Okay, how about
one more,
everybody else?
please?
Say it again.
Can we do one more?
You know what? Thank you. You're a mind reader. That's what I'm going to do. I'm going to shut up and have you folks try 15 over 3 plus the square root of 17.
Mm,
Oh, wait. Okay.
Did I do okay?
Yeah. I had messed up with my my squared problem. I just solved it. I just went from the square root of 17 from 3 and I just put negative 20. But I forgot that we were supposed to take them out after we
Yeah.
solved them.
And you know what? You can't combine those two because they're not like.
Right.
Under a radical and one isn't. And I'm just saying, give me a half a second, folks, because I am doing that old lady brain fart thing. And I want to just make sure that there's another type of problem that could be a little bit more involved. And I think, you know what, I think this is sufficient. So rationalizing the denominator, if there's two things, you have to use your conjugate. You know what, let's just do one more. What if I have 1 plus the square root of 2 over 1 minus the square root of 2?
Oh, jeez.
Wait, I have a after this one, I have a question of like how, like an example, like how we would do a different one of these.
What do you mean by a different one of these?
How would we rationalize something like radical 27 over radical 12? Like how would we rationalize something like that with two radicals?
With that one, if you have something like radical 27 over radical 12, the first thing I'd do is I'd look at that as radical 27 over 12. Can you reduce that fraction?
No.
No. Wait a minute. I think you can. Is there a number that goes into both 27 and 12?
3?
3. So wouldn't that reduce to the square root of 9 over 4? Which would be the square root of 9 over the square root of 4, or 3/2.
Yeah.
And we're done.
Okay, cool. I just didn't know how to do one like that. I was bugging for a second.
Always put it into a single fraction and see if you can reduce it, and then simplify the radicals and then decide if you have to rationalize. But with this one,
So that's been okay. That's what's been messing me up on the homework.
okay, well, let's go back to this one that I wrote. What we're
But
working out, go ahead.
for this one, wouldn't we? I was about to say, wouldn't we use the bottom?
Yeah, so what's the conjugate of the denominator?
It would be the 1 plus the square root of 2.
And whatever we do to the denominator, we have to do to the numerator. Denominator would become 1 squared minus radical 2 squared, which would be 1 minus 2. So my denominator is just negative 1. With this one, the numerator is the harder part. Let's look at the numerator. They're not conjugates. There's no shortcuts. We have to multiply that out.
So wouldn't that be 1 over, if you take that out of the 2, that would be 1. Wait,
In order to do that product, where we've got 2 things times 2 things, does anybody remember FOIL? First, outer, inner, last. If you don't remember FOIL, does anybody remember multiplying things using something like the box method?
yeah.
When
Oh,
we've got
box
2
method
terms, we
time.
either have to box or FOIL. I learned FOIL. I think, are you guys more familiar with boxes or FOIL?
I did FOIL.
I did box method.
Both take you to the same place. First, let's
So,
FOIL. First,
1.
1 times 1 is 1. Outer, 1 times the square root of 2 is the square root of 2. Inner, the square root of 2 times 1 is the square root of 2. Last, the square root of 2 times the square root of 2 is 2, giving me 3 plus 2 radical 2. So that's FOIL. Box, 1 times 1 is 1. 1 times radical 2 is radical 2. 1 times radical 2 is radical 2. Radical 2 times radical 2 is 2. And so when I combine, that also gives me 3 plus 2 radical 2. And so that's 3 plus 2 radical 2. So I get 3 plus 2 radical 2 divided by negative 1. And so if you wanted to, dividing by negative 1, wouldn't that give me minus 3 minus 2 radical 2?
So how would we do it if you put like X's in there?
We're not going to
To
put
get
X's
people
in there. I don't think with these we'll put X's in there for a while.
Okay, 'cause I just wondered if you like had like say like 5x squared over like radical x squared or something like that. Like how would you? I just didn't know if you would be near.
Okay, am I correct in assuming you're doing your homework right now and you're asking homework questions?
No. I'm not doing my homework right now. Like I'm on the Zoom.
Okay, if
But
you're
these are just things that are popping up in my head of like
okay,
to
let
make
me
sure I
do what
cover
you
all the
just
bases.
said. You said the square root of 5x squared over the square root of x squared.
Yeah.
Well, let me turn it into a single fraction first. Radical 5x squared over x squared. Can you simplify that fraction?
Wouldn't you just get rid of the x squared?
Yeah, so that's just radical 5.
Yeah.
Okay,
Will we ever have to do this with cube roots?
you're where I'm going next. So if
Okay.
everybody's all right with this conjugate thing, the next place we're going are other roots.
Oh my lord.
We said that the square root of a equals b if a is equal to b squared, and that's our square roots. If I have another root, we'll say that the nth root of a is equal to b if a is equal to b to the n. This is referred to as the nth root. The n is the index. The a is the radicand. And I apologize. The b is what we referred to as the nth root. Yikes. What's that all about? If I want the cube root of a, I apologize, I misspoke. I'm saying what number can I multiply by itself 3 times to get 8? What number times itself 3 times is 8? 2. 2 times 2 is 4, times 2 is 8. So we say the cube root of 8 is 2.
Wait, so how did you figure that out? Like
I
that's
said to myself, what can I multiply by itself 3 times and get 8?
oh
1 times 1 times 1 is 1. That doesn't work. 2 times 2 times 2. Yep, that's 8, so I've got it. What's
oh.
interesting is if I have an odd index, I can have a root, a negative under the radical.
Really?
Because if I were to take negative 2 times negative 2 times negative 2, if I had 3 negative numbers, wouldn't the product be negative?
Yeah.
So if the index is odd, you can have a negative radicand. So what if I ask for the fourth root of 81? Is there a number that I can raise to the fourth power and get 81? Is there a number I can multiply by itself 4 times and get 81?
Um,
9.
9 times 9 is 81, but that's 2.
3.
Oh, jeez.
Wouldn't it be 3? Because if I think 3 times 3 times
is
3,
9.
3, that's 9 times 9 or 81. So the
Oh, that's
fourth
pretty.
root of 81 is 3. If you're doing these with a calculator, on my calculator, I have x squared, and the second function above it is the square root. And then I have that caret up for a different exponent. And above that, do you see there's a square root symbol with a little x in the corner? That allows you to take a different index. So for the cube root of 81, with my calculator, I'm going to go, I'm sorry, for the fourth root of 81, I'm going to go 4. Then I'm going to go second caret up, and it gives me the square root symbol with a little x in the index. Then I'm going to type my 81, and it gives me that 3. So either with a calculator or by practicing your multiplication, what would be the fifth root of negative 32? What number can I multiply by itself 5 times and get negative 32? 32, I apologize. First of all, are we all in agreement this would have to be a negative number?
Yeah, because it's a negative.
Uh-huh. And so what number times itself 5 times is 32?
I hate to say it. Is it 6.4?
Nope. If you think 6 times 6 is 36, so we're going to be bigger than that. I'm saying something times itself. If I took 5 of one number and multiplied.
2.
Yeah, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this would be negative 3. And what's interesting is my rules for radicals hold. As long as they have the same index.
And what do you mean when you say that?
Well, I'm going to show you. If I
Okay.
have the nth root of A times the nth root of B, if the indices are the same, I can multiply the radicands. Likewise, if I have the nth root of A over the nth root of B, as long as those indices are the same, I can change it into a single fraction.
But that's only if they're the same, right?
Right. If they're not the same, there was a typographical error, it's beyond the scope of the course. And when we add and subtract like radicals, we're adding to the idea that for radicals to be like, the index has to be the same. So let's look at example. If I have the cube root of 7 times the cube root of 49, that would be the cube root of 7 times 49, which would be the cube root of 343, which is 7. I struggled with the 343. I didn't struggle with the 7. Is everybody all right? This is the cube root of 7 times the cube root of 7/3 would give me the cube root of 7 to the 3rd, which would just be 7.
Wait. I'm a little confused. Like with the second part of the problem that you wrote.
Oh, I'm just telling you how I came up with the 7 easily.
Oh,
I
okay.
recognized that 49, I'm sorry, I said 7 squared and I didn't write it. 49 is 7 squared. So if I multiply 7 times 7 to the second, I get 7 to the third. So look at another example. If I have the 4th root of 162 x to the 5th over the 4th root of 2x. Is everybody all right? The indices are the same. So I'll change that into a single radical. The 4th root of 162 x to the 5th over 2x. Is there anybody who can simplify that fraction for me?
Wouldn't it be like
Oh,
82?
did a good nap.
1 x to the 4th. And
I
with the
said
4th root
82.
of 81 we said is 3. And the 4th root of x to the 4th would just be x.
Wouldn't it be x squared?
No,
Or is
because I'm saying, what do I raise? If I look for the 4th root of x to the 4th, I'm saying, what do I multiply 4 of in order to get x to the 4th?
oh
It would
1?
just be x to the 1st, right?
So you got
Um,
4x to the 4th because you divided, so you subtract the 5 with 1?
Right. When I divide, I subtract exponents on the same variable. And for things like this, believe it or not, there's a slightly easier way of looking at it. But initially it sounds overwhelming. Can I turn the page?
Almost there.
Do I gotta go back? We good?
With that one.
Okay. Let's look at rational exponents. Rational or fractional exponents. What happens if I have x to the m over n? X to the m over n is going to be defined by, when I have a denominator, I draw a radical. I'm going to take the nth root, and the number in the numerator becomes an exponent, the nth root of x to the m, or it can be written as the nth root of x to the n. If I have x to the 1 over n, it just means the nth root of x.
Puppy, no, 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 stop peeing all over the place, puppy.
Could you mute yourself, whoever has a peeing puppy?
Oh, please.
If I have a fraction in the exponent, it means I have a radical. So for example, if I had 8 to the 1/3, it means I'm taking the 3rd root of 8, and the 3rd root of 8 is 2.
so basically, so what basically whatever the fraction is the nth root.
It if I have 81 to the 3/4, what that means is I'm going to take the 4th root of 81, the denominator is the index, and the numerator becomes an exponent. I'm going to cube it. So the
Wait,
4th
hold on
root
one
of 80
second, so I can.
Puppy, come here. Rosie, come here.
Danielle, can you mute yourself, please? What's the 4th root of 81? I think we said that was 3. And when I raise it to the 3rd power, I'll get 27.
So basically, whatever's in the bottom is the nth power.
The denominator is the index of the radical.
And then, so what would the numerator?
Exponent.
Oh, it's the exponent. Oh, okay. And then, so would equal 3. And then,
So what would I get if I took 36 to the 3/2?
so it would be the nth power of 36 with the exponent of 3.
2nd power root of 36 to the 3rd.
And then, so wouldn't that be 6?
6 to the 3rd, which would
Right.
be 6 times 6 times 6, or 36 times 6, which is 216.
Okay, I kind of understand this a little bit.
All right, then let's get a little trickier.
No, could we just stay here?
No. If I have 16 to the negative
Oh,
3/2.
oh, jeez.
Ay, 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 ay. First of all, what does it mean if my exponent is negative?
It equals 1.
I don't think it equals 1. Remember, negative exponent said we're going to make a fraction?
Yeah.
Exponent becomes positive in the denominator. And now this is telling me that that denominator's got a radical. I'm taking the square root of 16 and then cubing it.
Wait, so
What's
1
the square
over
root of 16?
16 to, and then that equals 1
So
over, and then 2.
What's the square root of 16?
So wouldn't it be 4?
Yep, and so now I have to take 4 to the 3rd. And so that gives me 1 over 64.
Oh, so basically, well, if it's negative, you write it as a fraction, and then do what we were doing for the problem before this one into the fraction, and then solve it from there, and that's how you get your answer.
And these are just exponents, so we can combine them with all of our exponent rules. What if I have 2y to the 1/5 to the 4th over y to the 3/10? Order of operations, we'd have to do our exponent first. So that'll be 2 to the 4th, y to the 1/5 to the 4th. 2 to the 4th is 16. Now I want to ask you folks, when I raise a power to a power, what do I do to those exponents?
You add them, right?
Nope.
Multiply.
Multiply. So 1/5 times 4 is 4/5. Oh, I'm sorry, that's 16y to the 4/5 over y to the 3/10. But now, in order to divide, what do I do with those exponents?
Subtract.
Subtract. So if I take 4/5 minus 3/10, I'm going to go old school and do it by hand. Common denominator is 10. So that's 8/10 minus 3/10, which is positive 5/10, which is
A half.
a half. So it's positive. So that's 16 to the 1/2. 16y to the 1/2. Or that's 16 times the square root of y.
I have a question.
Sure.
Okay, so when you were subtracting the fractions, how did you get the 8?
Common denominator is 10. In order to turn 5 into 10, I have to multiply it by 2.
By 2.
Because 2 times 5 is 10. It's what gave me my common denominator. And whatever I do, the
I'm sorry.
denominator I do to the numerator.
Okay, so then, so when you did the multiplying by 2, so you would have left the 3/10 the alone because it already was to the 10th. Okay.
Right. Oh gosh, and I'm just looking at the clock, and it's that time.
I think we can do one more.
Actually, I have a class at 12:30, and I have a lot to do between now and then. So we're going to stop here. You're going to find a lot more on the homework, and we'll look at any of those that you want at the beginning of next class. In addition, if anybody is doing the homework and they have questions, please feel